Good afternoon, ladies and gentlemen. Can everyone hear me? How did you guys find last week's semester test? Was the test fair? Was it difficult? Enough time? Easy, underprepared. So now you know how the exam will be as well. The exam will follow the exact same format and will be on the same difficulty level. So just a piece of admin. Just remember the submission date for the moon assignment is getting closer. So please pay attention to that. And also make sure you do it in time and contact me if you have any questions regarding the assignment. So remember the 20th of May. So that is almost. So are you guys ready to begin with today's lecture? So for today's lecture, we are going to talk about neutron stars, black holes, and compact objects with disks. So now throughout the semester so far, you guys have contacted me and asked a bit of questions about neutron stars and black holes. And today's lecture, we are going to try and answer most of those questions. So in last week's lecture, I showed you the diagram of how stars form. So we have our stellar nebula, one that we get an average star, a red giant, a planetary nebula, and then a white dwarf. When we have a larger star, so we have stellar nebula, a massive star that becomes a super red giant, that becomes a supernova, and from a supernova, it either becomes a neutron star or a black hole. And now we're going to learn what are the distinguishable factors that form these two objects. So for this chapter, we need to answer a few questions. The first one is, how does theory predict the existence of neutron stars? Secondly, how do astronomers know neutron stars really exist? Thirdly, how does theory predict the existence of black holes? And then lastly, how can astronomers know that black holes really exist? So, let me ask you guys this. How do we know that neutron stars actually exist? Any suggestions? Can everyone still hear me? So how do we know neutron stars exist? So in theory, we can predict neutron stars. But neutron stars can be directly observed, and the same with black holes. Black holes was originally theorized, but until recently, we actually imaged the first black hole. So gravity always wins. No matter how long a star struggles to withstand its own gravity, it must eventually exhaust its fuel and die by collapsing. These stars do not destroy themselves in a process became one of these three types of compact objects: white dwarfs, neutron stars, or black holes. A neutron star containing a little over one solar mass, compressed to the radius of about 10 kilometers, can be produced by type 2 supernovae. For example, a white dwarf has about the same mass, but is about the size of Earth. A neutron star's density is so high that physicists calculate that a material is stable only as a fluid of neutrons. Theory predicts that such an object would spin a number of times a second, be nearly as hot as the surface as the inside of the sun, and have a magnetic field a trillion times stronger than Earth's. So two questions should occur to you immediately. Firstly, how could any theory predict such a bizarre object? And then secondly, do neutron stars really exist? Neutrons were discovered in a laboratory in February 1932, and only 2 years later, in January 1934, Caltech astronomers Walter Baade and Fritz Zwicky published a seminal paper. They showed that some novae in historical records were much more luminous than the rest and suggested that these were caused by the collapse of a massive star's cores, resulting in an explosion they named supernova. The core of the star, they proposed, would form a small and tremendously dense sphere of neutrons. Zwicky coined the term a neutron star. Over the following years, scientists applied the principles of quantum mechanics to see if such an object was indeed possible. Neutrons spin in much the way that electrons do, which means that neutrons must obey the Pauli exclusion principle. In other words, if neutrons are packed together tightly enough, they can become degenerate just as electrons do. White dwarfs are supported by degenerate electrons, and quantum mechanics predicts that even denser mass of neutrons could support itself by pressure of degenerate neutrons. How does the core of a collapsing star become a mass of neutrons? Nuclear physics provides an explanation. As the supernova begins, the core collapses inward. If the collapsing core is more massive, then a Chandrasekhar limit of 1.4 solar masses, then it cannot reach stability as a white dwarf because the weight is too great to be supported by degenerate electrons. The collapse of the core continues, and atomic nuclei are broken apart by gamma rays. Almost instantly, the increasing density forces the free protons to combine with electrons and become neutrons by this reaction. So here we can see, as a result of each neutron is a neutrino. So you learned the previous chapter that bursts of neutrinos during supernova explosions help blast the envelope of the star away. So the star's core is left behind as a neutron star. So when we look at this image, which star produces neutron stars as remnants? What would you guys say? Which classification will start with a neutron star or end off as a neutron star rather? Type O, yes, type O is correct. If you look at that entire list, where would you say is the cutoff point? So everything below that will form a white dwarf, everything above that will form a neutron star. Type A is almost there. So usually from a type F star. So usually when you have a star that is 1 to 8 solar masses, that will become a white dwarf. But if you have a star that is between 8 and 20 solar masses, that will become a neutron star. So as you learned in a previous chapter, a star that begins its life with less than about 8 solar masses can lose enough mass to die by forming a planetary nebula and then leave behind a white dwarf. More massive stars also lose mass rapidly, but model calculations indicate they cannot shed mass fast enough to reduce their mass below the Chandrasekhar limit. So it seems likely that they must die in supernova explosions. Theoretical calculations suggest that stars that begin life on a main sequence of roughly 8 to 20 solar masses will leave behind neutron stars, stars even more massive than that, to form black holes. So this is what I can ask in a test and exam, and this is where your classification and definition comes in. If a star has 1 to 8 solar masses, it will form a white dwarf. 8 to 20 solar masses, a neutron star, and 20 solar masses and above, that will form a black hole. So the Chandrasekhar limit tells us at the end of a star's lifetime, when you start squeezing the material, degenerate electrons closer, and you squeeze more mass onto it, there's a point called the Chandrasekhar limit that is 1.4 solar masses. So anything above a 1.4 solar mass object is squeezed more tightly. And depending on how much mass above the Chandrasekhar limit is, depends on what will happen to it. So, for example, if you take our own sun, and when it is at the end of its lifetime, it becomes a white dwarf. That white dwarf still has 1 solar mass. But if you add more mass on top of that, so it becomes 1.4 solar masses, that means you can squeeze it more tightly, and that can become a neutron star. And if you add more mass on top of that, that will become a black hole. So in essence, you can really say a neutron star is 1.4 solar masses to 20 solar masses, to be more precise. And 20 solar masses and above for a black hole. Does that answer your limit? So that only tells us if you take a star that's above 1.4 solar masses, it will not end as a white dwarf. So how massive can neutron stars be? That is a critical question and a difficult one to answer because scientists don't know the strength of pure neutron material. They can't make such matter in laboratories, so its properties must be predicted theoretically. The most widely accepted calculations suggest the neutron star cannot be more massive than about 3 solar masses. If a neutron star were more massive than that, the degenerate neutrons would not be able to support the weight, and the object would collapse, presumably becoming a black hole. 2 of the most massive neutron stars observed have masses of 1.94 and 2.74 solar masses, evidence in favor of that hypothesis. How big are neutron stars? Mathematical models predict that a neutron star should be only 10 or so kilometers in radius, which combined with typical mass means it must have a density of about 10 to the power 15 grams per cubic centimeter. This is roughly the density of an atomic nucleus. So you can think of a neutron star as matter with absolutely all of the empty space squeezed out of it. On Earth, a sugar cube sized lump of this material would weigh more than 1 billion tons. So this is just to put things in perspective. So here a tennis ball in a roadmap illustrates the scale of a neutron star. Such an object containing slightly more mass than the sun would fit with room to spare inside a beltway around Washington, D.C. Simple physics, the same physics you have used in previous chapters to understand normal stars, predicts that neutron stars should not be hot, spin rapidly, and have strong magnetic fields. You have seen that contraction heats the gas in the star. As gas particles fall inward, they pick up speed, and when they collide, their higher speeds become thermal energy. The sun collapse of the core of a massive star to a radius of about 10 kilometers should heat it to 1 trillion degrees. Astronomers calculate that neutron stars should initially cool rapidly from the astonishing high temperatures because neutrinos can escape from their entire volume and carry energy outward. After a few years, neutron stars will cool down to a mere million degrees or so, and neutrinos won't be produced in bulk. From that point on, neutron stars should cool slowly because the heat can escape only from the surface. And neutron stars are so small they have little surface from which to radiate. The principle of conservation of angular momentum predicts that neutron stars should spin rapidly. All stars rotate because they form from a swirling cloud of interstellar matter. As a star collapses, it must rotate faster and faster. It conserves angular momentum. The sun collapsed to a radius of 10 kilometers. Its rate of rotation would increase from once every 24.5 days to more than 2,000 times a second. You might expect the collapsed core of a massive star to rotate in the range of 10 to 1,000 times a second. It is hard to understand how a neutron star could have a powerful magnetic field. All stars have magnetic fields, and some have fields 1,000 times stronger than the sun's. The field is frozen into the ionized gas of the star. And when it collapses into a neutron star, the field is squeezed down, concentrated, and made as much as 1 billion times stronger. Theory predicts the properties of neutron stars, but it also predicts they should be difficult to observe. Neutron stars are very hot, so from your understanding of blackbody radiation, you can predict they will radiate most of their energy in the gamma ray and X-ray part of the spectrum. Radiation could not be observed in the 1940s and 50s because astronomers could not yet put telescopes above Earth's atmosphere. Also, the small surface areas of neutron stars mean that they will be faint objects. Consequently, astronomers of the mid-20th century were not surprised that one of the newly predicted neutron stars had been found. Neutron stars were at that point entirely theoretical objects. Do you guys know who Professor Jocelyn Bell is? So you also see Professor Jocelyn Bell is a pioneer in the field of neutron stars, specifically pulsars. Pulsar is a subclass of neutron star that she discovered. So in November 1967, Jocelyn Bell, a graduate student at Cambridge University in England, found a peculiar pattern in the data from a radio telescope. So this radio telescope that she used was the Jodrell Bank radio telescope. So unlike other radio signals from celestial objects, this was a series of regular pulses. So one way you can imagine it is, let's begin back a little bit of background information. So 1967, they didn't have modern computers like we have today to display it. How do you guys think these recordings were made? So in this case, it is literally a piece of paper that's connected to a mechanical pen. So if you've ever seen in movies those old polygraph tests that they've done, and you have your needle moving up and down on a piece of paper, you all have that image. So this is made on exactly the same principle. You have a needle and a piece of paper, and then it drew the information coming from the telescope. So in this case, it drew a signal that is repeatable every amount of time. So this was a series of regular pulses that repeated all over and over and over again. So at first, she and the leader of the project, Anthony Hewish, thought the signal was interference from earthly sources. But I found it day after day in the same place, in the same part of the sky, and clearly it was a terrestrial origin. So another possibility that came from distant civilization led him to consider naming it LGM for Little Green Men. But within a few weeks, the team found three more objects in other parts of the sky, pulsing with different periods. So the objects were clearly natural, and the team dropped the name LGM in favor of a pulsar, so a contraction of pulsating star. The pulsing radio source Dell had observed with a radio telescope was known as the first pulsar. As more pulsars were found, astronomers argued over their nature. The periods range from 0.033 to 0.75 seconds, and each one was nearly as exact as an atomic clock. However, months of observation showed that many of the periods were slowly growing longer by a few billionth of a second per day. Whatever produced the regular pulses had to be highly precise, nearly as exact as an atomic clock, but also gradually slowing down. Before we continue, do you guys know what an atomic clock is? So, let me explain. An atomic clock is the most accurate way ever to keep track of time and to keep time accurate. So in South Africa, there are six atomic clocks, and three of them is at the observatory where I'm involved at the Hartebees Radio Astronomy Observatory. So you get them in a few flavors, but it's usually the atomic clock can usually be also referred to as a methanol maser or a hydrogen maser. And basically, how it works is you have a vacuum sealed chamber, and then you pump in exactly one molecule of methanol or one molecule of hydrogen, and then you give it a slight electric current. And then that slight electric current lets that part, that molecule, oscillate up and down in that vacuum sealed chamber. So if it's moved from one side to the other side of the chamber, 1 second has passed exactly. So the atomic clocks are now accurate to about 10 to the power minus 15 of a second. So it's 0, comma, 15 zeros and then 1 of a second. So that's the most accurate way we can keep time on Earth. Some of the experimental atomic clocks, so there's actually people doing research in time, can now go up to 10 to the power minus 27th of a second, which is very amazing. Do you guys know why we need to keep track of time so precisely? So, in Europe, especially in France, there are the Bureau of Standards. So in a Bureau of Standards, that's where everything is standardized. So if you think about, if you define what is 1 kilogram, they have a piece of metal that is exactly 1 kilogram. So if you know what's 1 meter, they have 1 meter exactly measured to the smallest that we can. And for experiments on Earth that requires timestamps and perfect timing, we want to keep time as accurate as possible. So that is where we have atomic clocks, and all atomic clocks are also synced across the globe. So if you say, oh, you're on your computers and phones, auto update date and time for South Africa, that date and time setting, you are receiving that from the Hartebeespoort Radio Astronomy Observatory from the atomic clocks they have there. Isn't that amazing? So now we have pulsars in space that are even more accurate than the best atomic clocks we have. So it was easy to eliminate possibilities. Pulsars could not be ordinary stars. A normal star, even a small white dwarf, is much too big to pulse that fast. Nor could a star with a hot spot on its surface spin fast enough to produce the pulses. Even a small white dwarf would fly apart if it spun 30 times a second. The pulses themselves gave the astronomers another clue. The pulses last only about 0.001 second, placing an upper limit on the size of the object producing the pulse. If a white dwarf blinked on and then off in that interval, you would not see a 0.01 second pulse. That's because the point on a white dwarf closest to Earth would be about 6,000 kilometers closer than its center. And the light from that spot would arrive in 0.02 seconds before the light from the bulk of the white dwarf. As a result, a short blink would be smeared into a longer pulse. This is an important principle in astronomy. An object cannot change its brightness appreciably in intervals shorter than the time light takes to cross its diameter. If pulses from pulsars are no longer than 0.001 second, then objects cannot be larger than 300 kilometers in diameter and could be much smaller. Only a neutron star is small enough to be a pulsar. In fact, a neutron star is so small that it couldn't pulsate slowly enough, but it can spin as fast as 1,000 times a second without flying apart. The missing link between pulsars and neutron stars was founded in 1968 when astronomers discovered a pulsar at the heart of the Crab Nebula. The Crab Nebula is a supernova remnant, and theory predicts that some supernovae leave behind neutron stars. The short pulses and the discovery of the pulses in the Crab Nebula was strong evidence that pulsars are neutron stars. So how do we model a neutron star? So as you have noticed before, scientists often work by building a model of a natural phenomena, not a physical model made of plastic and glue, but an intellectual conception of how nature works in a specific instance. The astronomer's model may be limited and incomplete, but it helps them organize the understanding. So the modern model of a pulsar has been called the lighthouse model, and we will notice three important terms. So to think about it, you have now a star at the end of its lifetime that's about 4 to 8 solar masses. It collapses in on itself. It forms a neutron star. So the star was a couple of thousand or even 100,000 kilometers in diameter. It's now less than 300 kilometers in diameter. And it's spinning a couple of thousand times around its own axis in just a second. So it basically looks like a lighthouse. So as it collapses and spinning around, it has immense magnetic fields, and a piece of its surface still radiates a bit of energy. And as it spins around its own axis, it kind of looks like a lighthouse that is spinning around. So pulsar does not pulse, but rather emits beams of radiation that sweep around the sky as the neutron star rotates. If the beams do not sweep over Earth, the pulses will not be detected by Earth's radio telescopes. Secondly, the mechanism that produces the beams involves extremely high energies and is not fully understood. And lastly, modern space telescopes observing from Earth's atmosphere can image details around young neutron stars and even locate isolated neutron stars whose beams of electromagnetic radiation do not sweep over Earth. Do you guys have any questions so far? Any questions? So how do pulsars evolve? So when a pulsar first forms, it is spinning fast, perhaps 100 times a second. The energy it radiates into space comes from its energy of rotation, so it blasts beams of radiation outward. Its rotation slows, so the average pulsar is apparently only a few million years old, and the oldest are about 10 million years old. Presumably, older neutron stars rotate too slowly to generate detectable radio beams. You can expect that a young neutron star should emit powerful beams of radiation. The Crab Nebula is an example. Only about 960 years old, the Crab pulsar is so powerful it emits photons all across the electromagnetic spectrum, radio, infrared, visible X-ray, and gamma ray wavelengths. So in this image, we can see high-speed images of the Crab Nebula pulsar show it pulsating at visual wavelengths and X-ray wavelengths. The period of pulsation is 33 milliseconds, and each cycle includes two pulses as the two beams of unequal intensity sweeps over Earth. So here we can see the visual image. The pulsar blinks twice each cycle. Here we can see the main pulse. Here we can see the secondary pulse in light intensity. Here we can see in X-ray the first pulse and then the second pulse. The most energetic pulsars produce short wavelength photons and disperse at visible wavelengths. The Crab Nebula pulsar is young and powerful, and it produces visible light pulses. So does another young pulsar called the Vela pulsar, located in the southern hemisphere constellation Vela. So in this image here, we can see here's the center of the Milky Way, the Vela pulsar, the Crab Nebula. We can see here the Majinga pulsar and another blazar over here. So here we can see how it evolves. So here we can see a young pulsar. And here we can see a radio jet, like a lighthouse beam, sweeping away from it. Compared with most pulsars, the Vela pulsar is fast, pulsating about 11 times a second. And like the Crab Nebula pulsar, it's located inside a supernova remnant. And its age is estimated to be relatively young, so 20 to 30,000 years old. The Fermi Gamma Ray Space Telescope, or in short, the Fermi Telescope, has detected a new kind of pulsar that pulses in pure gamma rays. It is not clear how these pulses are produced, but because gamma rays are extremely short wavelength, high energy photons, the process must involve very high energies. At least one of those gamma ray pulsars is located inside a supernova remnant that's only about 10,000 years old. So this is how the Fermi telescope looks like in space. The electromagnetic energy in a beam is just a small part of the energy emitted by a pulsar. Roughly 99.9% of the energy flowing away from a pulsar is carried as a pulsar wind of high-speed atomic particles. This can produce small, high-energy nebulae near a young pulsar. So in this image, we can see the effects of a pulsar winds can be seen at X-ray wavelengths. The high energy gas of the winds is sometimes detectable as it is the interaction of the winds with the surrounding gas. And not all pulsars have detectable winds. You might expect to find all pulsars inside supernova remnants, but the statistics must be examined with care. Many supernova remnants probably do contain pulsars, but their beams never sweep over Earth. Also, some pulsars move through space at high velocity, quickly leaving their supernova remnants behind. Nearly 2,000 pulsars are known, and some are located in binary systems. These pulsars are of special interest because astronomers can learn more about the neutron star by studying the orbital motions of the binary. Also, in some cases, mass can flow from the companion star onto the neutron star, and that produces high energy violence. The first binary pulsar was discovered in 1974 when astronomers Joseph Taylor and Russell Hulse noticed that the pulse period of the pulsar PSR B1913 plus 16 was changing. The period first grew longer and then grew shorter in a cycle that took 7.75 hours. Thinking of the Doppler shift seen in spectroscopic binaries, the radio astronomers realized that a pulsar had to be in a binary system with an orbital period of 7.75 hours. When the orbital motion of the pulsar carries it away from Earth, astronomers see the pulse period lengthen slightly, so redshift. Then when a pulsar rounds its orbit and approaches Earth, they see the pulse's period shorten slightly, and thus a blue shift. The resulting graph of radial velocity versus time was then analyzed to find the shape of the pulsar's orbit. So analysis of the pulsar showed that a binary system consists of two neutron stars, one with which is silent, separated by a distance roughly equal to the radius of our sun. So here is the center of mass of the two objects, and here is the orbit of the pulsar. And here we can see that pulse over hours and how it repeats as it orbits around the center of mass. So yet another surprise hidden in the motion of the pulsar. In 1916, Einstein's general theory of relativity described gravity as a curvature of spacetime. Einstein realized that any rapid change in the gravitational field should spread outward at a speed of light as gravitational radiation. Taylor and Hussel were able to show that the orbital period of the binary pulsar is slowly growing shorter because the stars are radiating orbital energy away at exactly the rate expected for gravitational radiation, and so are gradually spiraling toward each other. So normally binary stars are too far apart and orbit too slowly to emit significant gravitational radiation. Taylor and Hussel won a Nobel Prize in 1993 for their work confirming general relativity using binary pulsars. In 2016, it was announced that a laser interferometer gravitational wave observatory, or LIGO, that we talked about in a previous lecture, it makes the first direct detection of gravitational radiation, or another word for that is gravitational waves. Dozens of pulsars have been found orbiting stars of various kinds. By analyzing the Doppler shifts in their pulse periods, astronomers can estimate the masses of the neutron stars. Typically, masses are about 1.4 solar masses as predicted by theory. In 2004, radio astronomers announced the discovery of a double pulsar. two pulsars that orbit each other in only 2.4 hours. One spins 44 times a second and the other spins once every 2.8 seconds. The system is a pulsar jackpot because the orbits are nearly edge on to Earth. And powerful magnetic fields and a gas trapped in the fields eclipse each other, giving astronomers an opportunity to study their size and structure. Furthermore, the theory of general relativity predicts that these pulsars are emitting gravitational radiation so that their separation is decreasing by 7 millimeters per year. The two neutron stars will merge in 85 million years, presumably triggering a violent explosion. In the meantime, the steady decrease in orbital period can be measured, giving astronomers another test of general relativity and gravitational radiation. The gravitational fields of neutron stars are so strong they can be sites of titanic violence. And an astronaut stepping onto the surface of a neutron star would instantly smush into a layer only 1 atom thick. If you dropped an apple onto the surface of a neutron star from a large distance, it will hit with an impact equivalent to a megaton nuclear bomb. In general, a particle falling from a large distance to the surface of a neutron star will release energy equivalent to 0.2 mc squared, where m is the particle mass at rest and c is the speed of light. So here in this image, we can see this binary pulsar system. So here we can see the neutron star and the star, and here we can see the pulses as it sweep across Earth. So in this next image, we can see in image A, at visual wavelengths, the center of the cluster is crowded with stars. In image B, in the ultraviolet, one object stands out. And an X-ray source is consisting of a neutron star orbiting a white dwarf. And then in image C is an artist's conception showing matter flowing from the white dwarf on an excretion disk around a neutron star. So your knowledge of pulsars suggests that newborn pulsars should blink rapidly, and old pulsars should blink slowly. In fact, the handful that blink the fastest may be quite old. The current fastest known pulsar, it pulses 716 times a second and is slowing down only slightly. A number of other very fast pulsars have been found. They are generally known as millisecond pulsars because their pulse periods and therefore the periods of rotation are around a millisecond. This rapid rotation produces some fascinating physics. If a neutron star 10 kilometers in radius spins 716 times per second, then its equator must be traveling at almost a sixth of the speed of light. Because a pulsar's period is so precise, astronomers can detect tiny variations by comparing the observations with atomic clocks. When astronomers checked pulsar PSR B1257, they found variations in the period of pulsation, much like those caused by the orbital motion of a binary pulsar. However, in this case, the variations were much smaller, and when they were interpreted as Doppler shifts, it became evident that a pulsar was being orbited by at least two objects with planet-like masses of 4.1 and 3.8 Earth masses. The gravitational tugs of these planets make the pulsar wobble about the centers of mass of the system by no more than 800 kilometers, producing the observed tiny changes in period. So here we see a neutron star, the two planets orbiting it, and here we can see how it periods wobbles due to the tug of war of the gravity of these two planets. So ladies and gentlemen, that was neutron stars. Do you have any questions? You guys still okay? Awesome. So You guys are probably all familiar with this image. And this is the first image of a black hole, right? So now we're going to discuss where black holes fits into this. So now we have done from stellar nebula, red giant, planetary nebula, white dwarf, or stellar nebula, massive star, super red giant, supernova, and a neutron star. So the only thing left in this diagram is our black hole. So let's look at a history of a black hole. So the first idea of a black hole was first proposed by an English astronomer, John Michell, in 1784. So Michell's simplistic calculations assumed that such a body might have the same density as the sun, and concluded that such a body would form when a star's diameter exceeded the sun's by a factor of 500, and the surface escape velocity exceeds the speed of light. So he mathematically and theorized the existence of a black hole already in 1784, which is quite astonishing. And then in 1915, Albert Einstein developed the theory of general relativity, where the theory shows that gravity influences the motion of light. And in the image below, you can see a picture of Einstein in his early 20s. So one thing interesting, let's go back one slide. For what did Albert Einstein won the Nobel Prize in Physics? Any ideas? Yes, you are correct, for the photoelectric effect. So if you ask why is Einstein famous, most people would say E equals mc squared, or general relativity, or special relativity. But he actually won the Nobel Prize for the photoelectric effect. So in 1905, Albert Einstein determined that the laws of physics are the same for all non-accelerating observers, and that the speed of light in a vacuum was independent of the motion of all observers. This was the theory of special relativity. It introduced a new framework for all of physics and proposed a new concept of space and time. Einstein then spent 10 years trying to include acceleration in the theory and published his theory of general relativity in 1915. In it, he determined that massive objects cause a distortion in space-time, which is felt as gravity. So with this theory of general relativity, Einstein created or developed the Einstein field equations. So this right here is probably the only derivation I'm going to show you in this course. So don't memorize the derivation. I'm not going to ask it in a test and exam. It's just to show you where it comes from. So he developed the Einstein field equations, but he didn't have solutions for these equations. So we start by noting that energy is the line integral of force with respect to distance. So here we have kinetic energy, and it's line integral of F over ds. So when F is the force of direction of displacement, ds and s is the distance over which force acts. And then using Newton's law in its right of the differential form, we have F equals d mv over dt. So this, you can use F and we plug it into this equation. So then we can rewrite the kinetic energy in this form. So note that the velocity limits c, so the speed of light. So at c, time dilation becomes 100% and distances in the direction of motion shrink to 0. Hence, a body at this speed will not experience time or distance, and so its velocity is set as the upper limit. So now we can use integration by parts to solve this equation, and that gets mc squared minus m initial c squared. So the result shows that it connects so that we have So no, you don't need to know this. This is just background information. So the results show that the kinetic energy of a body is equal to the increase in its mass as a consequence of its relative motion multiplied by c squared. So we can rewrite mc squared as this equation. So in the kinetic energy is decreased so that k equals 0, the body will be stationary, but it will still possess m initial c squared. In other words, the body contains initial energy. So when stationary relative to its frame and will have initial mass, this is called the rest mass, and it is shown as this, where the initial energy is this. So this then completes the derivation of E equals mc squared for a body at rest. And for a moving body, its total energy is given by the following equation. So this is where the derivation comes from of E equals mc squared. So no need to memorize this, no need to know this, it's just part of the background explanation. So after Einstein published his theory, Karl Schwarzschild found the solution to the Einstein field equations, which describes the gravitational field of a point mass and a spherical mass. A few months after Schwarzschild, Johannes Drost, a student of Hendrik Lorentz, independently achieved the same result for point mass. So here is the Einstein field equations. So you don't need to know this at all. This is just background information. So here we have the Ricci curvature tensor, the scalar tensor, the metric tensor, cosmological constant, light speed in a vacuum, stress energy tensor, and Newton's gravitational constant. So then, Stephen Hawking gave a more solid mathematical understanding to a concept of a black hole. And let's go back one slide. So since the 1970s, Stephen Hawking did the majority of his work into black holes. So this is the Event Horizon Telescope and the location of the telescopes in this network. These telescopes were selected because they can all observe at X-ray frequencies. Then they use a technique of very long base interferometry that we have talked about in an earlier lecture that can create a virtual telescope that is the size of the distances between these telescopes. That means you can create a very large virtual telescope. So in the 1970s, it was theorized that a black hole would look something like this. With the help of Stephen Hawking and with his theories, and people from the Event Horizon Telescope, a simulation was created to see what a black hole might look like if we would image it. And this was the result of the simulation. And what we can see here, inside the black hole, this is the event horizon. The event horizon is the point of no return. So if you're outside the event horizon, you can still escape the gravity of a gravitational pull of a black hole. If you're inside it, you can't escape it. So this is infalling matter onto the black hole, moving into the event horizon. So this is the faster it's moving around, the more thermal energy you have, and it emits X-rays. This is part of the Doppler shift. So this part that's more brightly is moving this way towards Earth. On this side is moving away from Earth. So that's why this is seen as more bright. So when the first image was taken, this was the result, which shows it is actually spot on compared to the simulation. And it shows our understanding of black holes to this far actually works, and we can image it. You guys still following, still happy with my explanation? Awesome. So now we can talk about the escape velocity of a black hole. So suppose you threw a baseball straight up. How fast you throw it it is not to, how fast must you throw it if it's not to come back down? Of course, gravity will always pull back on the ball, slowing it. But if the ball is traveling fast enough to start with, it will never come to a stop and fall back. Such a ball will have an escape velocity from Earth or escaped Earth. So the escape from Earth in a spaceship would have to leave Earth's surface at 11.2 kilometers per second. But if you could launch a spaceship from the top of a tower, so let's say 1,000 miles high, the escape velocity will only be 10 kilometers per second, because the higher you are away, the further you're away from the central point of mass, and the less energy you need. So for Earth, that is 11.2 kilometers per second. And you get it by V escape, so you get it by using this equation and then just solving for V. So when you look at SpaceX launches, we put it in kilometers per hour. The escape velocity is 27,000 kilometers per hour. So if you could make an object massive enough or small enough, an escape velocity could be greater than the speed of light. Albert Einstein's theory of special relativity, published in 1905, says that nothing can travel faster than the speed of light. So even photons, which have no mass, would be unable to escape. And such a compact, massive object could never be seen because light could not leave it. Long before Einstein or relativity, the Reverend John Mitchell, a British gentleman astronomer, realized this peculiar consequence of Newton's law of gravity and motion in 1783. He pointed out that an object 500 times radius than the sun, but of the same density, would have an escape velocity greater than the speed of light. Then all emitted from such a body would be made to return towards it. So Mitchell didn't know it, but he was talking about a black hole. If the core contains more than 3 solar masses, when it collapses, no force can stop it. It cannot stop collapsing when it reaches the density of a white dwarf, because degenerate electrons cannot support that weight. It cannot stop when it reaches the density of a neutron star, because not even degenerate neutrons can support that weight. No force remains to stop the object from collapsing to 0 radius. An object collapses, its density and the strength of its surface gravity increase. If an object collapses to 0 radius, its density and gravity become infinite. So mathematicians call such a point the singularity. But in physical terms, it is difficult to imagine an object of 0 radius. Some theorists believe that a singularity is impossible, and the laws of quantum physics must somehow hold the collapse at a radius of roughly 10 to the power 20 times smaller than a proton. Astronomically, it seems to make little difference. So that's why you get a 0 on your calculator, as an error on your calculator when you divide by 0. And that's why when you were always taught you cannot divide by 0. Because if you in fact divide by 0, that means you are collapsing the object's radius to 0. If the contracting core of a star becomes small enough, the escape velocity in the region of space around it is so large that no light can escape. This means you can receive no information about an object or about the region of space near it. Because it emits no light, such region is called a black hole. If the core of an exploding star collapsed into a black hole, the expanding outer layers of the star would produce a supernova remnant, but the core would vanish without a trace. In 1916, Albert Einstein published a mathematical theory of space and time that became known as the general theory of relativity. Einstein treated space and time as a single entity called spacetime. His equation showed that gravity could be described as a curvature of spacetime, and almost immediately the astronomer Karl Schwarzschild found a way to solve Einstein's equations to describe the gravitational field around a single non-rotating electrically neutral lump of matter. That solution contained the first general relativistic description of a black hole. And non-rotating electrically neutral black holes are now known as Schwarzschild black holes. In recent decades, theories such as Roy Kerr and Stephen Hawking have found ways to apply the sophisticated mathematical equations of general relativity, electromagnetism, and quantum mechanics to describe charged rotating black holes. For this discussion, the differences are minor, and you may proceed as if all black holes were Schwarzschild black holes. Schwarzschild solution shows that if matter is packed onto a small enough volume, then space-time curves back on itself. Objects can follow paths that lead into the black hole, but no path leads out. So nothing can escape. Because not even light can escape, the inside of the black hole is totally beyond the view of an outside observer. The event horizon is the boundary between that isolated volume of spacetime and the rest of the universe. And the radius of the event horizon is called the Schwarzschild radius. A collapsing stellar core must shrink inside the Schwarzschild radius to become a black hole. Although Schwarzschild's work was highly mathematical, his conclusion is quite simple. The Schwarzschild radius depends only on the mass of the object. Sorry, sir, you explained the difference between the different black holes again. So there are two black holes types. So the one is when you think about a black hole that is non-rotating, electrical neutral. That is a Schwarzschild black hole. If you have a black hole that is not electrically neutral and is rotating, that's a different kind of black hole. But for this module, we will only be working with Schwarzschild black holes. So therefore, when we speak about a black hole in this module, we refer to it as just a black hole. Does that make sense? It's a pleasure. So in this formula, G is the gravitational constant, M is the mass in kilograms, and C is the speed of light in meters per second. And a bit of arithmetic shows the one solar mass black hole has a Schwarzschild radius of 3 kilometers. The 10 solar mass black hole has a Schwarzschild radius of 30 kilometers, and so on. Every object has a Schwarzschild radius determined by its mass, but not every object is a black hole. For example, a radius of about 1 centimeter, meaning that a giant vacuum cleaners that would Can you hear me better now? Okay, cool. So it is a common misconception to think of black holes as giant vacuum cleaners that will eventually suck in everything in the universe. A black hole is just a gravitational field, and at a large enough distance, its gravity is no greater than that of a normal object of similar mass. So if the sun were replaced by one solar mass black hole, the orbits of the planet would not change at all and still continue happily along. So this figure illustrates this by representing gravitational fields as curvature of the fabric of spacetime. Normal uncurved spacetime is represented by a flat plane, and the presence of a mass, such as the star, curves the plane to produce a depression. This extreme curvature around a black hole produces a deep funnel-shaped surface in its graphic representation, and you can see from the graphs that the gravity of a black hole becomes extreme only when you approach close to it.
Now you can check off another misconception that may strike you as silly. Because of special effects in movies and TV, some people think black holes should eventually look like funnels. Of course, the graphs of the strength of gravity around black hole looks like funnels, but the black holes themselves are not shaped like funnels. If you could approach a black hole, you might be able to see hot gas swirling inward, but you wouldn't be able to see the black hole itself. Before you can search for real black holes, you need to understand what theory predicts about a black hole. To explore that idea, you can imagine leaping feet first into a Schwarzschild black hole. If you were to leap into a black hole of a few solar masses from a distance of 1 AU, the gravitational pull would not be very large, and you would fall slowly at first. Of course, the longer you fell and the closer you came to the center, the faster you would travel, and your wristwatch would tell you that you fell for about 2 months by the time you reached the event horizon. Your friends who stayed behind could see something different. They would see you falling more and more slowly as you came closer to the event horizon, because explained by general relativity, time slows down in curved space-time. This is known as time dilation. In fact, your friends would never actually see you cross the event horizon. To them, you would fall more and more slowly until you seemed hardly to move. Generations later, your descendants could focus their telescopes on you and see you still inching closer to the event horizon. However, would have sensed no slowdown and would conclude that you had reached the event horizon after about 2 months. Another relativistic effect would make it difficult to see you with normal telescopes. As light travels out of a gravitational field, it loses energy and its wavelength grows longer. This is known as gravitational redshift, and as you fell towards the black hole, your friends would need to observe you at longer and longer wavelengths to detect you. While these relativistic effects seem merely peculiar, other effects would be quite unpleasant. If you were falling feet first, you would feel your feet, which would be closer to the black hole, being pulled in more strongly than your head. This is a tidal force, and at first it would be minor. But as you got closer to the black hole, the tidal force would become very large. Another tidal force would compress you as both your left and your right side fell towards the center of the black hole. For any black hole with a mass like that of a star, tidal forces would crush you sideways and stretch you lengthwise long before you reached the event horizon. So this image just explains graphically what we see. So leaping feet first into a black hole, a person of normal proportions on the left would be distorted by tidal forces on the right, long before reaching the event horizon around a typical black hole of stellar mass. So tidal forces would stretch the body lengthwise while compressing it laterally. Friction from this distortion would heat the body to high temperatures. The frictions from such severe distortions of your body would heat you to millions of degrees, and you would emit X-rays and gamma rays. Some people have suggested that it's possible to travel through the universe by jumping into a black hole in one place and popping out in another somewhere far across space. That might make for good science fiction, but tidal forces would make it an unpopular form of transportation, even if it worked. You now know how to find a black hole. Look for a strong source of X-rays. It may be a black hole into which matter is falling and being heated. The first X-ray telescopes reached orbit in the 1970s, and that allowed astronomers to begin searching for evidence of black holes. They tried to find one or more objects that were obviously black holes. That very difficult search is a good illustration of how the unwritten rules of science help scientists understand nature. The black hole alone is totally invisible because nothing can escape from its event horizon. But if matter flows into a black hole, it will whirl through an accretion disk and become hot enough to emit X-rays before it reaches the event horizon. An isolated black hole in space will not have much matter flowing into it, but a black hole in a binary system might receive a steady flow of matter transferred from the companion star. This suggests you can search for black holes by looking closely at X-ray binaries. Some X-ray binaries, such as Hercules X1, contain a neutron star, and they will emit X-rays much as would a binary containing a black hole. So you can tell the difference in two ways. If the compact object emits pulses, you know it's a neutron star because the neutron star has a solid body within which powerful magnetic fields are generated. As the neutron star rotates, the magnetic field emits beams that sweep around the sky, producing pulses as they pass across Earth. A black hole inside its event horizon cannot emit regular pulses like those from a neutron star. Another clue depends on the mass of the object. If the mass of the compact object is greater than about 3 solar masses, it cannot be a neutron star, it must be a black hole. The first X-ray binary suspected of harboring a black hole was Cygnus X1, the first X-ray object discovered in the constellation Cygnus. It contained a supergiant star of spherical type B0 and a compact object orbiting each other with a period of 5.6 days. Astronomers suspected that the X-rays were emitted by matter from the star flowing into the compact object. That object is invisible, but Doppler shifts in the spectrum reveal the motion of the B0 star around the center of mass of the binary. From the geometry of the orbit, astronomers were able to calculate that the mass of the compact object has to be greater than 3.8 solar masses, well above the maximum for a neutron star. To confirm that black holes exist, astronomers needed a conclusive example, an object that couldn't be anything else. Cygnus X1 didn't quite pass the test when it was first discovered. Perhaps the B supergiant that was not a normal supergiant and its portion of the system mass was incorrectly estimated. Or perhaps the system contained a third star. Either possibility would distort the analysis. At the time, astronomers could not conclusively show that Cygnus X1 contained a black hole. It took years of work to understand Cygnus X1. Further observations and analysis show that B0 star has a mass of 25 solar masses, and a compact object is about 10 times the mass of the Sun. The astronomers conclude that matter flows from the B0 star as strong stellar wind. Much of that matter gets caught in a hard accretion disk about 5 times larger than the diameter of Earth's orbit, of the orbit of Earth's moon. So the inner few hundred kilometers of the disk have a temperature of about 2 million Kelvin and hot enough to emit X-rays. So here we can see an artist's representation of the X-ray source Cygnus X1. So here we can see the 6 black hole binaries, and it shows the star type, the orbital period, and the mass of the black hole. So another way to confirm black holes are real is to search for evidence of their distinguished characteristics. So that is event horizons, and that search has been successful. So matter flowing onto a neutron star or into a black hole forms an accretion disk, and that can produce some surprising phenomena, and astronomers are just beginning to understand these peculiar effects. So now we're going to start talking about the compact objects with disks and jets. So observations show that some compact objects, when we talk about a compact object, that is either a white dwarf, a neutron star, or a black hole. So observation shows that some compact objects are emitting jets of gas and radiation in opposite directions. And these jets are similar to the bipolar outflows ejected by protostars, but much more powerful. And that leads us to gamma ray bursts. So the Cold War played a minor part in the story of neutron stars and black holes. In 1963, a nuclear test ban treaty was signed. And by 1968, the United States was able to put a series of satellites into orbit to watch for nuclear tests that were violations of the treaty. A nuclear detonation emits gamma rays, so the satellites were designed to watch for bursts of gamma rays coming from Earth. The experts were startled when a satellite detected about 1 gamma ray burst a day coming from space. When those data were finally declassified in 1973, astronomers realized that a burst might be coming from neutron stars and black holes. And these bursts are known as gamma ray bursts, or GRBs in short. So in this image, we can see, altered by gamma ray detectors on satellites, observers used one of the VLI 8.2 meter telescopes on a mountaintop in Chile to image the location of a GRB only hours after the burst. The image at the top left shows the fading glow of the eruption, and the image at the top right, recorded 13 years before, reveals no trace of an object at the location of the GRB. The Hubble Space Telescope image at the bottom was recorded a year later and reveals a very faint distant galaxy at the bottom of the GRB. Gamma ray bursts are hard to study because they occur without warning and fade quickly. But starting in 1997, new satellites were put into orbit to detect gamma ray bursts. The data show that there are two kinds of gamma ray bursts. Short bursts last less than 2 seconds, but longer bursts can go on for tens of seconds up to several minutes. Special space observatories now can detect bursts, quickly determine their location in the sky, and immediately alert astronomers on the ground. When telescopes on Earth swiveled to image the locations of the bursts, they detected fading glows that resembled supernovae. Stellar interior models indicate that a star more massive than some upper limit of about 20 solar masses can exhaust its nuclear fuel and collapse directly into a black hole. Models showed that a collapsing star would conserve angular momentum and spin very rapidly, slowing the collapse of the equatorial parts of the star. The poles of the star would fall in quickly, and that would focus beams of intense radiation and eject gas that would blast out along the axis of rotation. Such an eruption has been called a hypernova. So how does this happen? So first we have the collapse of the core of a massive star begins along its axis of rotation. And because the rotation of the star slows the collapse of the equatorial region, so equatorial over here, within seconds the remaining portion of the core fall in from north and south parts. And then beams of gas and radiation strike surrounding gas and generate beams of gamma rays along the rotation axis. And then the gamma ray burst fades in seconds, and a hot accretion disk is left around a black hole. So short gamma ray bursts, on the other hand, don't seem to be associated with hypernovae. Some repeat, and these repeating bursts seems to be produced by neutron stars with magnetic fields 100 times stronger than that in a normal neutron star, dubbed magnetars. These objects can produce bursts of gamma rays when shifts in the magnetic field break the crust of the neutron star, causing star quakes and release large amounts of energy. Not all short gamma ray bursts are produced by magnetars. Some bursts have occurred in parts of distant galaxies where you would not expect to find the young massive stars that produced magnetars or hypernovae. And the afterglows don't resemble fading supernovae. These bursts may be produced by the merger of two neutron stars or a neutron star and a black hole that orbited each other, radiated orbital energy as gravitational radiation, and spiraled into each other. Such a collision would cause a violent explosion as the two objects merge to form a new larger black hole. The gamma ray bursts and fading afterglow from neutron star plus black hole merger should be different from that produced by the merger of two neutron stars. Could a gamma ray burst occur near Earth? The nearest known binary pulsar is about 3,000 light years from Earth. If a gamma ray burst occurred at that distance, the gamma rays would shower Earth with radiation equivalent to a 10,000 megaton nuclear blast, comparable to the full-scale nuclear war between superpowers. The largest single bombs ever made released less than 100 megatons of energy. The gamma rays could create enough nitric oxide in the atmosphere to produce intense acid rain and also would destroy the ozone layer, exposing life on Earth to deadly levels of solar ultraviolet radiation. Gamma ray bursts can occur relatively near Earth as often as every few 100 million years and could be one of the causes of the mass extinctions that showed up in our fossil records. So how do we detect these gamma rays? Because they're such high intensity, they move through everything that we know. So in our neighboring country, Namibia, is the HESS telescope. So what the HESS telescope does is, when the gamma rays enter Earth's atmosphere, it interacts with the upper atmosphere and never reaches the ground. So these telescopes observe the interaction in the upper telescope. So this is in the Gamsberg in Namibia and is also a very cool site to visit if you are ever in Namibia. So here is a image of a black hole and explains the different parts that we can observe. So to end off this lecture, physicist Brian Greene tweeted this when the first image of a black hole was released. It is hard to express how utterly remarkable and astonishingly delightful it is that mathematical scribblings can predict something as bizarre as a black hole, and then looking to the skies with sufficient diligence, we found them. Neil deGrasse Tyson tweeted, "Scientists, we've produced the first ever image of a supernova black hole, a supermassive black hole 55 million light years away." And response is, ooh. "Scientists, we've concluded that humans are catastrophically warming Earth." And response is, "That conflicts with what I want to be true, so it must be false." Bill Nye, the science guy, tweeted, "How can we see a star that gives off no light of its own? Take a look." And this was just released after the death of Stephen Hawking in the same year. So it's quite sad that he couldn't see his work, his life's work, being imaged. And that, ladies and gentlemen, is our lecture on neutron stars and black holes. Do you have any questions? So, ladies and gentlemen, for tomorrow's lecture and the rest of the semester, do you guys guess what topics remain? We have now learned about stars, how stars formed. We've learned about compact objects such as neutron stars and black holes. So now we have two themes remaining. The next theme that we are going to discover is, if we zoom out a little bit, how does galaxies form and what govern the processes of galaxies? And then after that, we are going to return and focus on our own solar system. And we're going to talk about how planets form and what governs planets. So, ladies and gentlemen, this is our lecture for today. Tomorrow we will talk about the Milky Way galaxy. So have a wonderful day, and I will see you all tomorrow.